Okay, so today's class setup is a little different because I've already been made aware that there wasn't going to be anybody showing up to class in person, nor would anybody be showing up synchronously online. So I'm just going to record myself going through today's notes here and get that video posted. So this works out well for me because it saves me a little time. Also, this is a pretty difficult topic to present, so I'm actually grateful to not have to write all of this on the board. So, okay, so to quick recap of where we've been. Um, we've been focusing on solving Ax equals B by iterative methods in a case where A matrix A is symmetric, positive, definite. We had seen the method of steepest descent, where we would have an iterate xk and then go in a direction of a residual b minus axk a certain distance to figure out the next iterate, and that didn't work so well because each residual direction, was not necessarily independent of prior directions, so progress was slow. We improved on that last time, developed the Lanczos iteration, in which each residual is orthogonal to all previous residuals. So Lanczos iteration ends up having this form, where each iterate xk is in terms of the initial guess, plus a linear combination of orthogonal vectors, or orthonormal vectors, and the residuals are scalar multiples of each of these orthonormal vectors that populate qk. During a Lanczos iteration, you compute this tridiagonal matrix tk, which helps you to get the each new iterate. So this is definitely a substantial improvement over steepest descent, but there's still improvements that ought to be made because, for one thing, unlike steepest descent, this is not in the form of a non-stationary iterative method. In a true non-stationary method, each new iterate is equal to the previous one plus a vector that takes you in a certain search direction. We don't have that here. Each iterate is expressed in terms of the initial guess. Um, and the problem with that, the reason why that's a bad thing, is to compute each of these iterates, we're solving this system of equations here, where the matrix Tk is k by k. That means the matrix is getting bigger and bigger with each iteration. So each iteration is significantly more computationally intensive than the last. Um, and we don't want that. We want an iterative method in which the amount of computational effort for each iteration is about the same. And the steepest descent, for all of its faults, did satisfy that criterion. So we want to try to rework this in such a way that each iterate can be expressed in terms of the previous one, um, and therefore not have this growing amount of work um, for each iteration. So, um, so what we're going to do is, okay, actually, before I get into that, um, I mean, one thing I did not get into with Lanczos iteration is that because this matrix TK is symmetric and tridiagonal, that nice structure that TK has um, can make it possible to get a true non-stationary iteration where each iterate comes from a previous one. Um, it would take a certain amount of algebra to make that happen, uh, but um, but conceivably something that can be done. But that's not the only issue that makes Lanczos um, not the best choice for a symmetric positive definite Ax equals B problem. Um, is even though the columns of QK are constructed so as to be orthonormal, because we're dealing with floating point arithmetic, in practice, these columns turn out to not really be orthonormal after all. If you were to take inner products of them, like go ahead and compute QK transpose QK as the iteration proceeds, you'd find that at first it would be identity to machine precision, but then it would start veering away from identity because of this loss of orthogonality. One thing that people have done with Lanczos to fix that is some sort of reorthogonalization scheme. That what you could do is, as you compute each new column of this matrix, you can explicitly orthogonalize it against the previous columns. Now that incurs an additional overhead, so that further degrades efficiency. And people have worked on how to carry that efficiently, like not necessarily reorthogonalize every time, but just in certain situations. So there are things that can be done to make this method more practical, but we're not going to explore those. Instead, we're just going to come up with a whole other method that actually is very widely used for solving symmetric positive definite systems, and it's called the conjugate gradient method. The Lanczos method is useful for a lot of things beyond ax equals b. It's useful for certain eigenvalue problems, like computing the extremal eigenvalues, the largest or the smallest of a symmetric matrix. And there's other applications besides that, because it generates a orthonormal basis for a Krylov subspace. And there are many problems throughout numerical linear algebra that can be solved very nicely with a basis like that. But what we're going to do is try to develop a better iterative method, and that's going to be conjugate gradient. So what we're going to do is we're going to take a closer look at this system of equations that has to be solved during each iteration of Lanczos algorithm, and see what we can do with it with this system to solve this and generate iterates more efficiently than Lanczos can now. Okay. So what we're going to do is we're going to examine how this system changes from one iteration to the next. So if we consider this for after k iterations in the same system after k plus 1 iterations, how to express one system in terms of a previous one. So what I can do is the matrix tk plus 1 is built from tk by adding on another row and another column. And because all of these T matrices are tridiagonal, there's only 3 non-zero entries that we're adding on here. So this extra column we're adding on, keep in mind EK is the kth column of the identity matrix. So it's all zeros except for a 1 in the last position. So this vector here is all zeros except beta k is in the last position. Here we have a transpose of that. So this portion of a row we're adding on is also all zeros except, again, beta k in the last position. And then we add on one more diagonal entry that's alpha k plus 1. If you look at the notes from last time, TK is a tridiagonal matrix that has alpha 1, alpha 2, and so forth down the diagonal, and then like beta 1, beta 2, down the etc. down the super diagonal and the subdiagonal. So we're just adding on the latest alphas and betas. And then yk plus 1, we break it down into the first k elements being this vector tilde yk, and then some element psi k plus 1 that gets added on the end. Now I want to emphasize here, this vector yk tilde is not the same as this yk up here. And that's actually one of the reasons why Lanczos cannot easily be expressed as a typical non-stationary method, where you can get each iterate in terms of a previous one, because these two vectors are not the same. We'd actually like to rework this solution process so that we can get each vector easily from a previous one just by adding on one more element. All right. And so we are working towards that goal. So if I write out this system, but in a k+1 case, in terms of this these block structures that we have here, then this is what we get. So it's actually these two equations right here. So here we have a vector equation with k elements. So that comes from multiplying the top blocks of tk+1 with this vector here, and setting that equal to beta naught E1, the first k elements of it. And then from the bottom blocks, multiplying with this vector, we get this single equation. This is a scalar equation right here, set equal to 0, because that's the last element of the right-hand side. Now, so what I can do is rewrite this system of equations here, because here we have a tridiagonal matrix, and then here I have a vector, a column vector, that is 0 in every entry except for the last one. So I can think of this system as this system, where notice I have tk tilde rather than tk. So tk tilde is a modification of tk, where what I've done is first used this equation to get a formula for psi k+1, because psi k+1 is the last unknown, but notice it features in both equations. So if I solve this equation for psi k+1, then I can use it to eliminate psi k+1 from this equation. So my only unknown left is this yk tilde. If I can solve for that, then I can just go ahead and use this to compute my last unknown. So basically, I'm eliminating one unknown from the system of equations. So, so by taking this formula for psi k+1 and substituting it in here, then I get this system where the modified matrix tk tilde is tk minus this term. And notice I have this outer product, ek transpose. So what does this mean? This right here is a matrix that is entirely 0 except for the last row, last column. So the kk element is set equal to this, because ek transpose, remember ek is a vector that's all zeros except for a 1 in the k position. So this right here is a matrix that is all zeros except for a 1 in the kk position, and then that gets multiplied by this scalar to put that in this number in that last position. So tk tilde is nothing more than tk with this value subtracted from the kk element. All right. So another way of putting it is tk tilde is called a rank 1 update of tk, and that's true because a matrix of this form, an outer product, is a matrix of rank 1. So in other words, what I've been able to do is reduce this system of equations, k+1 equations, k+1 unknowns, to this system that is a k by k system, k equations, k unknowns, with the last unknown worked out here. Now, as I mentioned before, last time, tk is tridiagonal, symmetric positive definite. So it has this factorization, LDLT factorization. That was covered back in section 3.3 on special matrices. And because it's tridiagonal, the factorization has a fairly simple form. Because remember, when you factor a banded matrix through Gauss elimination, your LU factors inherit the bandwidth of the original. So TK has a lower bandwidth of 1. Therefore, LK has a lower bandwidth of 1. And LK is unit lower triangular. So we just have these 1s, and then we have these values down the subdiagonal. And then DK is just a diagonal matrix. And so this factorization is going to be quite helpful to us. Now, we've seen that TK and TK tilde are the same, except for the KK entry. And it turns out that because we only differ there, okay. Oh, we seem to have a mistake here. It should be TK tilde, not TK minus 1 tilde. Of course, now I'm wondering, like, have I made that same mistake in the book? And yes, I really am in another window going to find out. Okay, sorry. You know how I am. I can't help that. Oh, yep. Sure enough, it's there too. Dang it. Okay. Anyhow, so what's interesting about this difference between these two is that TK tilde has almost the same factorization. The LK matrices in the two factorizations are exactly the same. It's just the diagonal part that is different. So we call that DK tilde. And DK tilde and DK are, again, almost the same. It's just this last diagonal entry that will be different. Okay, so how does this help us? So I'm going to define these vectors, WK and WK hat. And I'll define them this way, both with LK transpose times YK, which is used to compute X, the iterate XK, and then YK tilde, which is part of computing the iterate XK plus 1. This is the first K elements of the vector YK plus 1. So then, here's my system, the left side of my system that I'm solving for YK, and I replace TK by its LDLT factorization. But now this vector, this matrix vector product, which is a vector, is defined to be WK. And then that's set equal to the right side that we've had all along, and that's beta naught E1. And then similarly, TK tilde, YK tilde, because it has almost the same factorization, we just have DK tilde in place of DK, and then WK hat in place of WK. So we have YK tilde satisfying these very similar systems. So now what I can do is suppose I take this system and this system, multiply both sides on the left by LK inverse to move LK inverse to the other side. Well then, because these vectors are the same, and then I'm multiplying them both by the same matrix, LK inverse. So it turns out that this matrix vector product and this matrix vector product are both equal to this. So these are the same. Now, it's already been established that DK and DK tilde, these are diagonal matrices, and they are the same except for the last diagonal entry. So what that means is WK and WK hat are also the same except for their last entries. So this is a consequence of TK and TK tilde being so similar, only being different in this one spot, that causes this near equality. Now, if we look at the previous formula we had for xk, I've just moved this x naught term over to the left side. That's equal to qk yk. And now I'm going to write yk in terms of wk using this definition here. So now I have this formula for xk minus x naught in terms of wk. Now, if I take this system that was first mentioned up here and look at the k plus 1 case, and I break it down like I did a system of TK before using the block structure, then I have this. What's different this time is TK was tridiagonal, but LK plus 1 is lower triangular, and this is diagonal. So this whole matrix is also lower triangular. So we get to 0 here, and that's going to be very helpful to us. And then I break WK plus 1 down, as was done before, that we have WK tilde here, and then the last element tacked on. So I do the same thing as I did with a system of TK and TK plus 1, where I carry out the multiplication of these top blocks with this vector to get this system, and then, which is simpler in this case because we have this 0 here, and then these lower blocks multiplied by this vector that gives me this equation. Now, what do we have though? LK, DK, WK tilde, which is newly introduced here, is beta naught E1. But then I look back up here, LK, DK, WK with no tilde also equals beta naught E1. What that means is WK and WK tilde have to be equal because they solve their solutions to the same system, same matrix, same right-hand side. So that's something that we really want. That because of the problem was, if I go back to the original system we were solving, we like to think of the system involving TK plus 1 as building on top of this one. The trouble is, this vector right here is known to not be the same as yk. So we can't just take this solution and then tack one element onto it. But by working with the LDLT factorization instead, we're in a similar situation here, where we like to have this vector build off of this one. And it turns out we can, because WK and WK tilde are equal. So all we're doing is figuring out what is the last element to tack on with each new iteration. So here's how we benefit from that. If I look at xk plus 1, so that's equal to the initial guess, and then we have our qk plus 1, and then this right here is yk plus 1, and that was worked out down up here, but now we're using k plus 1 instead of k. Now, and what I'm doing here is I'm breaking this up into this vector that has the first k elements of it, which we know is wk, and then a 0. And then we have the last element down here. And then I take a matrix, capital QK plus 1, and do a column partition of it. Here I have the first k columns, which are just a matrix, capital QK, and then the new column that's added onto it. And then LK plus 1 inverse transpose, I write as a block structure. And because it's because LK plus 1 and therefore LK are lower triangular, so our transposes are upper triangular, this k by k block of the inverse is just LK inverse transpose. So it has this block structure where zk is some vector as yet unknown. And then I and then I distribute this product rewritten in this form through this sum of vectors here. So now I have this part coming from here, and then this multiplying this over here. Here I carry out this matrix times this vector, which gives me this. And I still have this over here. Then I carry out this matrix times this vector, which gives me this. But notice I'm going to compare this with the first two terms here. They're exactly the same, except here we have k plus 1 as the subscript throughout. Here we have k. In other words, this right here is xk. So now I have what I always wanted from the beginning. Each iterate is written in terms of a previous iterate plus this new term. instead of expressing each iterate in terms of the initial guess. So now we've taken a big sort. Now we have the makings of a true non-stationary iterative method. The challenge now is to have an efficient way to compute this every time with each iteration, and expending about the same amount of effort. Right now, we don't really have that because this matrix is growing with each iteration, and so is this one. So we still need to be able to work these out efficiently. But at least now we have xk plus 1 in terms of xk, which we didn't have before. All right. So now what I'm going to do, notice we have this matrix qk lk inverse transpose. So I'm going to define a new matrix to be equal to that. So that's, I'm going to call it pk tilde. And then if I take this equation and multiply both sides of it on the right by LK transpose, right? So PK tilde will have this column partition. These are its columns. And then here I have LK transpose. LK is lower triangular, so its transpose is upper triangular. Oh, I want to point out, in the book, there's a typo. There's a transpose up here that shouldn't be there because this matrix has already been transposed. And that would be equal to QK, which has this column partition here. So now, because of the nice structure of this matrix being bidiagonal, if I write out this matrix equation, all of this, column by column, then I get the following. P1 tilde is just Q1. And then I have this linear combination of only two columns of this matrix are equal to Qj. So, so what exactly can I do with that? Because, okay. I swear to God, if I found another mistake in here. Okay. So, well, I think what I might want to do is add an intermediate step to better explain this. Okay, so I'm going to make a copy of this. Okay. All right, so I have xk is equal to, all right, I need to edit this first. So I'm going to reduce all the indices by 1. Okay. All right, so I have this from what I had on the previous page, but QK LK inverse transpose, that's PK tilde. So that's all I've done. I've replaced this with PK tilde down here. But multiplying PK tilde by EK, all that does is just take the kth column of PK tilde, which is little PK tilde right here. So, so each iterate, new iterate, is equal to the previous iterate plus some scaling factor times this vector. And I'm actually going to write it a little differently. So instead of WK PK tilde, I have this different scaling factor, nu k, times PK with no tilde. So these P vectors, I'm going to call my search directions because that's a direction that gets me from one iterate to the next. Okay. And then we just have a scalar nu k to work out. So what we have here is, if you look at this equation right here, each new search direction is a linear combination of the residual, because remember residual is a multiple of each Q vector, and the previous search direction. And then the very first search direction is just a multiple of a corresponding residual. Okay. Now, our search directions are going to be multiplied by some appropriate scaling factors anyway. So we're just going to set P1 equal to R1, our first residual. And then each new search direction will be equal to the corresponding residual plus some multiple of a previous search direction. So now, this is my new non-stationary iterative method where each search direction is determined by this relationship right here. Now, the method is not complete, though, because I haven't said anything about how we actually figure out these scalars, the nu k here and the mu k here. Because recall in steepest descent, the search directions were just the residuals, and then we had a formula for a scaling factor that we would put here. We don't have that yet, but now we're going to get that. So what helps us get that is if I take this matrix we had before, PK tilde, and write out what it is in terms of its definition. So PK tilde transpose A PK tilde is written out this way from that definition. And then I apply the transpose here. But then this right here is TK. But TK had this LDLT factorization, which now I substitute in here. But then this cancels out. That's identity. And that's identity. I'm left with DK. In other words, PK tilde transpose A PK tilde is a diagonal matrix. Now, if I look at what's happening here, entry by entry in this matrix equation, that's saying that the dot product of one of these vectors, like if I say pi tilde, the dot product of pi tilde vector with a times pj tilde is equal to 0 if I is not equal to j, and it's non-zero if I equals j. Now, remember if the dot product of two vectors is 0, those vectors are orthogonal. We don't have that here. We have pi tilde dot product with a times pj tilde. So we call that a orthogonal or a conjugate. So it's a different notion of inner product than the standard one. So I said before last time that we'd like to have our search directions all be orthogonal, but that's unrealistic. So we're settling for the next best thing. They're not orthogonal, they're a orthogonal. So we're still all linearly, very much linearly independent. So another way of looking at it is this, that the search directions of P's satisfy this relation. So if I didn't have this A here, then we would just say very orthogonal. But because the A is put in here, they're A orthogonal. So because the search directions are A conjugate and they're expressed in terms of the residuals, which are gradients. Remember, its steepest descent, residual was the negative gradient of a function we were minimizing to solve Ax equals B. The method that we're developing is called the conjugate gradient method, or a method of conjugate gradients, because our search directions involve gradients and they're A conjugate. Now, we still need these constants that help us get our iterates, our x's, and also our new search directions. And now that we know that the search directions are A orthogonal and the residuals themselves have to be orthogonal, these are criteria that help us get formulas for these scaling factors that we need. Okay. Now, I'm going to scroll back to equation 2. Where is it? Okay. This equation right here, what I'm going to do with this is multiply both sides of this by A, and then subtract the result from B, our right-hand side. That gives me this equation here because each residual is B minus A, like RK plus 1 is equal to B minus A XK. So this equation falls out from carrying out these manipulations. Then I take the inner product or dot product of both sides of this equation with RK, because RK transpose RK plus 1 would be 0. And that gives me a formula for nu K. But I'm not going to settle for this formula. What I'm going to do here is, because here I have this inner product, but these vectors being different. But what I can do is keep in mind that I have this relationship between the residuals and search directions. So I can express RK in terms of PK and PK minus 1. So I go ahead and do that. I've replaced RK with this difference here. But the search directions are A conjugate. This transpose APK is 0. So this term goes away, and I'm left with this. Now, if I go back to this equation right here, I still have these unknown scaling factors I need to find, and I multiply both sides of it by A. And I take the inner product of both sides of PK minus 1. I have this relationship from the left side. That's going to be 0. And then I have this on the right side. So I can rearrange this to solve for mu K. So now I have all the scaling factors I need. I have this formula for nu K here and mu K here. So I technically have a complete algorithm. But the reason why I'm still not done, unfortunately, is I want to try to minimize matrix vector products. Here I have to compute A times PK. Here I need to compute A times RK. So that's 2 matrix vector products each iteration. And I'd rather not do that. That's expensive if I can help it. So, so I'm going to modify this formula here. Okay, so what I do with this formula is, okay. All right. So how I got these manipulations, if I look at um, this right here, this equation right here, and I reduce all of the indices by 1, this gives me a way of taking A times any search direction and expressing it as the difference of 2 consecutive residuals. Because what I'm having down here, actually, I'm going to add another step so you can see it more easily. All right, I'm going to take a previous formula and paste it in there. Okay, but then I'm going to rewrite this numerator here as A pk minus 1 transpose. Okay, keep in mind, what's the transpose of this? It's going to be pk minus 1 transpose A transpose. But A is symmetric positive definite, so A transpose is A. So this becomes this. But then, if I go back to this equation right here, like I said, A times the search direction can be expressed as the difference of 2 consecutive residuals. That's how I get to here, and I have to divide by the scaling factor nu k minus 1. But residuals are orthogonal. So rk minus 1 is orthogonal to rk, so this term is going to go away. The minus and the minus will cancel, and now I have this. So now I don't have A in the numerator at all. So that's one matrix vector product eliminated. But I can go even further, because down below I have this dot product. So then I express pk minus 1 in terms of the corresponding residual in the previous search direction. But this is A orthogonal to pk minus 1. So the inner product of this and this is 0. So that term goes away. And now I have this. But again, A times the search direction can be expressed as the difference of 2 consecutive residuals. The residuals are orthogonal, so rk minus 1 transpose rk is 0. So now I'm left with this. So now I have no matrix vector products in the definition of mu k at all. It's a nice simple formula involving the dot products of 2 consecutive residuals with themselves. Yeah. All right. Okay. So now that I have this formula that's as simple as I can get for mu k, and then I have this formula for nu k, I could put everything together, and I have the conjugate gradient algorithm right here. So I choose my initial guess, I form my first residual, and then what I do is, for the first time around, my search direction is just my first residual. I compute this matrix vector product for convenience because I need it in more than one place. I compute my nu k using the last formula that I arrived at for that. Now that I have nu k, I can compute my new iterate and also my new residual. Um, so then the next time around, I'll use this formula to get my next search direction using this scaling factor mu k with my simplest formula here, and this process continues. And notice there's only one matrix vector product per iteration. That's the most expensive part right here. Okay. All right. So this is equivalent to Vilanchos' algorithm. The iterates xk that it produces in exact arithmetic would be the same, but it'll do it a lot more efficiently because each iterate is expressed in terms of a previous one using just tacking on a scaled vector. Also, we don't have the concern with Lanczos about the loss of orthogonality of the orthonormal vectors. So it's more numerically stable in that sense. And each iteration has about the same computational expense, which is not true of Lanczos. So it's very much an improvement on that. So this is quite an effective method for symmetric positive definite systems, although there's still work to be done. Okay. Because if a matrix is ill-conditioned, it's necessary to perform what's called preconditioning to try to get a better conditioned system and then apply conjugate gradient to that. So in fact, a MATLAB function is called PCG, preconditioned conjugate gradient, because you wouldn't normally use conjugate gradient without a preconditioner. I'm not really going to get into preconditioning here, though. So what's interesting about conjugate gradient, we think of it today as an iterative method, but it wasn't treated that way when it was first developed back in 1952. Okay. All right. Because with the search directions guaranteed to be linearly independent, but you're functioning in n-dimensional space. So once you get to n search directions, you're not going to find any more. So the inventors of conjugate gradient, Hessnes and Stiefel, thought of conjugate gradient as a direct method, like as if you were using Gauss elimination and back substitution, because n iterations would be enough to get the exact solution aside from rounding error. But in practice today, it's used for very large systems of equations where you would not want to carry out n iterations, but hopefully it would converge rapidly enough that you could get a sufficiently accurate solution in a lot fewer than n iterations, especially if you have good preconditioning. All right, so this is the state of the art for solving general symmetric positive definite systems, particularly for the cases where A is large and sparse. Okay, so that concludes the discussion of iterative methods for symmetric positive definite systems. So on Tuesday, I'll talk about variations on conjugate gradient for more general systems, either just symmetric and not positive definite, or just plain unsymmetric. So there you have it.